Alright students, so we are solving limit problems here now using algebraic techniques. Alright, so the techniques specifically that we're going to be looking at are direct substitution, factoring, and multiplying by the conjugate. Also not listed there, but there's direct substitution, a slight variation on that is dealing with piecewise functions. So, alright, let's get after it. So as it turns out, some functions are really nice. Alright, sorry you can't see me doing the air quotes, but by nice I mean continuous at our point of interest. Now, we'll talk a little bit later about what it means for a function to be continuous at a point, but just roll with me on this. Some functions are really nice, and it is really simple to find the limit at a point or at many points or anywhere. So for instance, like this really hastily drawn function of x is x squared plus 1. Let's say you do the limit of f of x as x approaches, I don't know, 3, okay? Well, first off, the scale is all messed up. So there's 3, and so it would go up to like 9, and this is really off. But anyway, okay. So you see the function's really nice. There's no gaps or jumps or like asymptotes or anything. It's just literally right there where you would expect it. It's at, oh my gosh, did I really put 9? Okay, just ignore that plus 1. It should be 9 plus 1, but whatever. Okay, so I was thinking x squared, but that's fine. You should plug in the value. All right, what about 4? Kick over a notch. Well, that's going to occur at x squared. Again, remember, ignore the plus 1. So 4 squared, so 16. We're at 5. Okay, all the way up there. So at 5 squared, 25. So, sorry, still kind of thinking about that plus 1 there tacked on the side. Anyway, so here we go. So for these functions and lots of the other really nice ones, the limit of f of x as x approaches a is f of a. I know maybe in previous episodes I said that those are not the same thing, and that's true. That what they are not, they don't mean the same thing. This means what is the function value at a. This means what does the function approach as x approaches a. But sometimes they do approach the same thing, or the left side approaches what the actual value is. And if that's the case, if that's the type of function that you're dealing with, you can solve those by what we call direct substitution, or by directly substituting in a into x, and that is really nice. We like that. So directly substituting the value into the function. So what are some examples of nice continuous functions? Well, linear functions, y equals mx plus b. There's no gaps or jumps or asymptotes. Quadratic functions, ax squared plus bx plus c. In fact, any polynomial, x cubed, x to the 4th, x to the 5th, or to the 10th. Sine and cosine are well-behaved, nice continuous functions. Some rational functions, it kind of depends on what the point of interest is, where we're trying to find the limit. So, all right, so here's one. Here's a rational function. They say find the following limit of 2x minus 9 over negative 2x squared plus 3 as x approaches 3. So the go-to thing, if you don't have if you want to graph this and go through all that fun stuff, great, go ahead. Or just try plugging in 3 and see what happens. Okay, so I'm going to plug in 3 for the numerator, plug in 3 for the denominator. Maybe we'll come up with a win here. So we have negative 3 in the numerator, and then 2 times 9, so that's negative 18 plus 3, so that's going to be negative 15 in the denominator, so negative 3 over negative 15, so 1/5. So hey, that's awesome. Just plugging in that value for that limit. Don't even have to bother with typing it in and looking up the graph, doing a table. Just give direct substitution a try first time. If it works, great. If it doesn't work, well, we've got other tools in our toolbox that we'll develop for that. Like I said, sines and cosines, really nice. Plug in that negative 3 pi over 2. See what happens. In this particular case, you know that 3 pi over 2 is one of your values on your unit circle. You can use that to evaluate the sine and cosine of the angle. This one turns out to be negative 6 pi. So if you want to roll with that, you can. All right. So of course, not everything's that nice. Sometimes you have these guys, piecewise functions, sort of if-then functions. So f of x equals x if x is less than or equal to 1, and it equals negative x squared plus x plus 1 if x is greater than 1. So let's kind of think about this. In this region right here, f of x equal to x, that's clearly linear. When x is greater than 1, then we're looking at some sort of quadratic, some sort of like parabola thing opening down because the leading term's negative. I don't know what this looks like off the top of my head, but I know the linear is going to go through there. Of course, actually it goes to the origin, but whatever. It's linear just for the purposes of showing you visually what I just said. Quadratic opening downward, it might go down like that, it might go down like that, it might go down like that, but remember it's only for values that are greater than 1, so there's an open circle there at 1, and I don't know exactly if it's lined up with where this one ends or not, okay? But we can find that out real quickly. So like I said, we're not sure which one of these locations it is. So the way we evaluate the limit of a function that is piecewise, and we've got the left and the right, well, what does this mean? The limit of f of x as x approaches 1 from the left. Okay, so that means from values less than 1, so like negative 3, negative 2, negative 1, 0, and then all the way up to positive 1. And you think, okay, which one of these situations covers that? Is it the x less than 1 or the x greater than 1? Well, it's going to be the x less than or equal to 1 region. I put less in here, but it should be less than or equal to. So that means effectively this statement right here, limit of f of x as x approaches 1 from the left, for this function can be written as x for f of x, because that's the function rule there. And let's just try direct substitution. So the limit of x as x approaches 1 is 1. And in fact, that's the answer. Okay. This plus here means from the right. And that would be, for instance, x values of 3, then 2, then 1.5, then 1.3, then 1.2, then 1.1. So that's this quadratic term here. So we can do the limit of negative x squared plus x minus 1. Or sorry, plus x plus 1. That's a really poorly written plus symbol as x approaches 1. And once again, direct substitution. Let's give it a shot. Negative 1 squared plus 1 plus 1. And that's going to be 1. Great. So we've got 1 for the limit as f of x approaches 1 from the left and from the right. So the two-sided limit's 1. We actually can figure out what this is. No need for a graphing calculator. No need to figure out how to get that graphing calculator or Desmos or anything else. How to do piecewise functions. We just kind of think through it and then do direct substitution, and that's great. This is the same type of thing. If we have the limit as we approach a number from and has a little minus sign, that means the left. That means this region right here. Plug that in for your f of x. From the right, plug that expression in. And if the numbers that you get there are the same, like we had in that previous problem, then the two-sided limit approaches that number. If they're not the same, then, as we said previously, then if the value that you're approaching from the left and the right is different, then the two-sided limit does not exist. Okay, so that handles the piecewise. Let's try some more situations where we just do direct substitution. Direct substitution is great, just plug it in. So here we have the limit of x squared plus x minus 2 all over x minus 1. I'm going to plug in 1 for the numerator, or for x in the numerator, and 1 for x in the denominator, and I get 0 over 0. Alright, now just to remember, 0 in the numerator is okay. That's not a big deal. 0 divided by pretty much anything is 0. But if you have a 0 in the denominator, we don't like that. That operation is undefined division by 0. So what are we going to do? Well, let's factor this expression and see if we can simplify it. So as it turns out, x squared plus x minus 2 can be factored into an x minus 1 and an x plus 2. Remember that denominator is an x minus 1, so actually those would cancel. And so this whole entire limit statement here could be written as the limit as x approaches 1 of x plus 2. And then we're back to direct substitution. Plug in 1 for x, and we get 1 plus 2 is 3. So we were pretty much unable to directly substitute 1 in here, but through algebraic simplification, we're able to arrive at an exact answer. And this, in fact, is the correct answer, 3. All right. So factoring is one mechanism. There's really no need, I feel like, to do multiple examples of factoring. You've, by this point in your career, done lots of factoring. So always try direct substitution first. In this case, we have the limit of x minus 4 over 1 over 4 minus 1 over x. So sort of a complex fraction, a fraction of fractions, so to speak. And plug in 4, and I get 4 minus 4 in the numerator and 1 over 4 minus 1 over 4 in the denominator, and we don't like that. That's a 0 over 0, sad face. So we're going to try to do some simplification here, do some algebraic techniques. So let's find a common denominator in this denominator term. So and turn this whole thing into one fraction, and maybe something will work out for us here. So common denominator is going to be 4x. So I'll multiply this term here by x over x and this term over here by 4 over 4. The numerator here stays the same. Now I have x over 4x minus 4 over 4x. So that numerator is x minus 4. The denominator is x minus 4 divided by 4x. So what I'm going to do now is I'm going to write that numerator, x minus 4, and then instead of saying divided by the denominator, I'm going to say multiplied by, flip it, the reciprocal of the denominator, 4x over x minus 4. Those x minus 4's cancel. It simplifies to 4x. So now I'm going to rewrite that whole limit statement as the limit as x approaches 4 of 4x. Direct substitution for the win. 4 times 4, 16. Sorry, that is a really ugly looking 4. It kind of looks like an H actually. But anyway, 16 is your answer. Last problem. Here we go. Direct substitution, always give it a shot. Plug in 4. So 5 minus square root of 29 minus 4 over 4 minus 4. I can already see that denominator is going to be 0. We don't like that. So, yuck. Going to need to do some algebra manipulation here. So we're going to try the multiply by the conjugate technique, where remember the conjugate is the same binomial but with a plus instead of a minus, or a minus instead of a plus. So we have 5 plus the square root of all that stuff over 5 plus the square root of all that stuff. The reason why we do the multiply by the conjugate, and it's so helpful, is because that gets us to an a minus b times an a plus b situation, which, if you recall, is an a squared minus b squared situation. And a squared is going to be 5 squared, 5 squared please, that should be, anyway. And then square root of 29 minus x squared is just 29 minus x. So I think I fixed that at some point here. So anyway, next thing we'll do is I'm always going to leave that denominator in factored form, so just to let you know. I'll distribute that minus sign, so we have, yeah, I think I fix it here in a second. So this should be 5 squared, which is 25. So 25 minus 29 is a negative 4, and then a minus and a minus create a positive, so positive x. Again, the numerator still, the denominator still in factored form. So rewriting this negative 4 plus x as x minus 4 over x minus 4 times quantity 5 plus square root 29 minus x. Running out of room right down there. Actually, I never did fix that 25. Should be a 25 right there. So this x minus 4 cancels out. This x minus 4. I still have a 1 in the numerator here. This is 1 over all that stuff. So going back here to our original problem, the limit of this term becomes the limit. X approaches 4 of 1 over 5 plus the square root of 29 minus x. Direct substitution. So we'll note there. So I have 1 over 5 plus square root 29 minus 4, which is 1 plus 5 plus square root of 25. Square root of 25 is 5. So that's 1 over 10. All right. So that is solving some limits through algebraic tools, multiplying by the conjugate, and finding a common denominator to get simplify that fraction of fractions into just a fraction. Also factoring. We looked at piecewise, and we looked at good old direct substitution. Hope you enjoyed it. Thanks for watching.